Hi, everyone, and thanks for being here. And thanks to Xerox PARC for putting this on. Xerox PARC was really cool, and it's awesome to be a part of something that feels like a spiritual successor to that. So today we're going to be talking about SnarkyJS and the Mina protocol. Let's see. I'm Jack. This is Martin. We both work at the product team at O1 Labs. O1 Labs is a zero-knowledge proof engineering company. And today we're going to talk about the Mina protocol and SnarkyJS. So yeah, we'll talk about SnarkyJS first, then we'll give an example of a Fibonacci implementation, and then we'll make that recursive. And then we'll talk about the Mina protocol and where you can learn more. Also, sorry for some of the slides. They didn't quite export right from PowerPoint, but hopefully we can get the picture. So SnarkyJS is a TypeScript library for defining zero-knowledge proofs. And it's also the smart contract language for the Mina protocol. Here's some code. Don't worry about it. We'll go back to it in a minute. So everything is TypeScript. You can keep using the tools you're familiar with, like npm, prettier, ESLint, VS Code, whatever. And it's easy to learn. So it's actually so easy to learn that hopefully you can kind of figure it out without even having to look at documentation or anything. The IntelliSense support is really good, and it feels a lot like programming in normal TypeScript. It's also extremely powerful. And this is for two reasons. One is our proof system, which is Kimchi, and we can kind of, if you're curious, stop me and Martin after, and we'll talk about that. But we have totally trustless setup. We have custom constraints for Poseidon, elliptic curves, and encryption, and we can add more. Proof size is constant, it's recursive, and it's Plonkish, so we can add new features like dynamic array access. The other side of this is the SnarkyJS library. So this is what users actually interact with. And so TypeScript method chaining allows developers to think through their programs in a linear way, especially compared to some of the other zero-knowledge proof sort of tools that are out there. We can kind of see what this looks like. So this is a really simple example. We have isCorrectColor. This is a bool. We just call the AND method and pass in another bool as an argument. And what we get out is another bool. And we've got like equals, all sorts of different things. But it sort of makes it really clear to think about your data, think about how it has to change, and then see what comes out. The other thing that we have is custom circuit values. And so these provide a layer of abstraction that makes the data much easier to think about. What this looks like is we just extend circuit value, and then we basically define how we're going to turn structured values that are easy to make sense of into these underlying field representations. And then it also figures out how to take these values back out into things you can work with easily. So here's one for pegs on like a board game, but you can make them for anything. Finally, we have a lot of the stuff that you already need implemented in SnarkyJS. So what's included today? We have all sorts of types for things that you're used to, with more coming soon, like string. We have efficient Poseidon hash functions, efficient decryption and encryption, and efficient signatures. So all of these are done with custom constraints. We also have Merkle trees, a couple other things implemented in an experimental part of the API, and recursion, which makes recursive proofs easy. Why did we choose TypeScript? Well, because we're ecosystem focused. So lots of people here hopefully want to build crazy cryptography stuff, and you should totally do that. But some people maybe want to make products that do stuff that they don't know how to figure out themselves. And so we hope that they can just import your library and get started. We want to have code reuse that's as high as it is in the JavaScript ecosystem. So yeah, SnarkyJS, everything is in TypeScript. It's easy to learn, and it's extremely powerful. How does SnarkyJS actually work? Well, here it is in 5 sentences. There's a bit more, so again, come grab us after if you're curious. But it's a TypeScript library. All the information is represented in one of the SnarkyJS compatible types. All of these are eventually composed of fields. SnarkyJS provides classes and functions that are compatible with the field type or the circuit values that are composed from them. It can represent any operation on the field type as a Kimchi arithmetization. So anything that you do in SnarkyJS can become a part of this arithmetization, and then it can be proved. So when a user interacts with the SnarkyJS program, they can generate a zero-knowledge proof that their interaction was legal. How do smart contracts work? So developers write smart contracts in TypeScript, and they deploy just the verification key to a ZK app account on Mina. And we'll get into Mina in a little bit. So yeah, we just send a transaction with a verification key. It creates a new account. And then your interaction with this account is contingent on you being able to submit a valid proof with it. And so that's how you can constrain the account to sort of behave as a smart contract. So the user runs a smart contract in their browser, and they generate a zero-knowledge proof. And then they send it to Mina. And if the transaction is valid, or if the proof is valid, then all the associated state updates are committed. Let's go back one. Yeah, so into our proof, we get contract state, the arguments, and the state of the world. If the proof is valid, then we get a valid proof, and we get updates to the state of the world and the smart contract state. So those are committed if the proof is validated by the Mina blockchain. Here's kind of a rehash of that. How do ZK apps work? Well, you just install your smart contract in your UI repository, and you deploy, and that's it. It's all TypeScript, so you just put it on GitHub, Node, whatever you like, and it's a part of your front end, basically. I'm going to pass it off to Martin to talk about a Fibonacci example. He's got some code, so it should be pretty cool.
Cool. So just to lay out some groundwork, we're just going to implement the Fibonacci sequence in a ZK app. And this is a pretty simple example, but the whole point is just to demonstrate how you use ZK apps with Mina and how you use SnarkyJS. So just to lay out the groundwork, we're going to write a smart contract to calculate the number in the current Fibonacci sequence. And we're going to have two pieces of state. We're going to have n-2 and n-1. And then we're just going to initialize them at the beginning to 0 and 1. In addition to that, we're going to have an update method that takes in an input parameter n. And then the whole point is that we're going to add our two state variables together. We're going to get the Fibonacci number that we're currently at, and then we're going to compare it to this n value here. And then if those two values match, we're going to produce our ZK proof that's able to be submitted to the Mina blockchain, and then we're going to update our on-chain state. So to begin writing a ZK app, you first just declare a class in TypeScript, and you extend this smart contract class, which is provided to you by SnarkyJS. And this just declares like an empty ZK app. And so the next thing we want to start doing is start defining our on-chain state. And so you define your on-chain state by using this @state decorator. And if anyone just is a little rusty on TypeScript decorators, it just basically lets SnarkyJS add some additional features to your class variables or your functions after they've been declared. And so we use this @state decorator, and we're passing in this field type here. And so one thing that's important to note is that when you're defining your state on a ZK app, it must be implemented in terms of field elements. SnarkyJS provides a bunch of different types that are already implemented in field elements, such as booleans, ints, uints, public key, private key, signature. And as mentioned previously, you can define your own custom type by declaring a class and then extending circuit value, where you just define your properties in terms of field elements again. But the important thing to note is that when you're defining your on-chain state, it just must be defined in terms of field elements. And so when we have this on-chain state, on the blockchain concretely, it's going to be public and viewable by anyone. So if you insert any kind of value in here, if a user went to like a block explorer and they wanted to check out your ZK app, the values will be public. But you can also you can make commitments to values instead. So if you wanted to instead put a hash of a value instead, you can commit to a value without it being public for everyone. So next, we're going to define a deploy method. And this deploy method is just run when we first deploy our ZK app to the chain. And then this is usually just done to initialize the state that we want. And so in this case, it's pretty easy to read. We're just referring to our state there. And then we're using this .set call. And .set is how you set your on-chain state. And so we're just initializing it to 0 and 1 at the beginning. So now we want to start adding some behavior to our ZK app. And the way you do this is by defining methods on your class and then annotating it with this @method decorator, similar to how we did with state. So ZK apps can have multiple methods on them, and they all have their own logic. And you can define really as many as you want. You can also you can define how it's invoked. So when you as a developer are writing your ZK app, you can make certain assertions so that the proof generation will only happen when those constraints are met. So you can kind of control when it's invoked and who's invoking it. And then an important thing to note is that any input arguments to your methods are private by default. So when you invoke the method, this end argument coming in, it will only be known to the prover when you're actually generating the ZK proof, and it won't be, it won't be viewable by anyone once you actually submit it. So this is how we declare a method, and we're going to start defining some behavior. We're first going to get the current on-chain state. And so we create these two variables here, current n-2 and current n-1. And the way you get on-chain state is just by using this .get call. So you refer to your on-chain state, or you refer to the state you define in your class, and then you use this .get call. And what this is doing is just making like a network request, and then fetching the current state that your ZK app has, and then we just store it in these two variables here. So once we get our on-chain state, we want to start interacting with it. And in this case, since we're calculating Fibonacci numbers, we're just going to add these two state variables together to get this new state. And then we're going to assert that this new state equals the input parameter that we passed in. And so something that's cool with SnarkyJS is that with a lot of the library functions, this goes for assert equals, but also the .add call as well. It will generate constraints for you automatically. So if you're used to using something like circom, you'll use the operator to generate constraints for you. But in SnarkyJS, these constraints are automatically generated for you when you use these library functions. And something that's really nice, too, is that this current n-2 is of type field. And since we're using TypeScript, we have great support for IDEs. So when you're programming and you type in current n-2 and you hit dot, the IDE will show all the methods that are available, and it gives you like a nice developer experience and like a sense of code exploration while you're doing it. So here, we're just calculating the new state, and then we're making a constraint on it. And then finally, when we create our new state, and then we know that the assertion passes, we're just going to set our on-chain state. And so you can do this by using this .set call, and this was done with the deploy method as well. We get to this point where we know that the constraints pass, and then we just refer to our state again, and we call .set, and we pass in the on-chain state that we got before. So in this case, we're setting n-2 to n-1, and then we're setting n-1 to this new state. So we're kind of like shifting the window in this Fibonacci sequence. And so then once we invoke this method and all the constraints pass, ZK proof will be generated, and then we can submit it to the chain, and then our on-chain state will be updated publicly. So that's kind of like the structure of how you develop ZK apps. You define state, and you define a deploy method to initialize that state, or you can define other things like setting permissions. And you define methods to interact with that state and do some computation, do assertions, generate constraints, and then do the updates that you want that you submit to the chain. So that was a basic example, and we're just going to take it a step further and define the same thing but recursively instead. So SnarkyJS has this really powerful technique that Jack talked about, which was infinite recursion. And so the idea is we can generate these state updates and then just generate a proof instead. And then we can embed that state change in a proof within another proof. And we can just do this arbitrary amount of times. So instead of doing this step-by-step calculation for the Fibonacci sequence, we can just pre-compute n amount of sequences that we want. And then we can submit it to the chain and then just verify that it's correct there. And so to do this, this is what the code looks like. We use this ZK program primitive instead of smart contract instead that SnarkyJS exposes. And there's a little bit of like confusing code here, but I'm just going to focus on the important points here. One thing that's different about ZK program than extending your smart contract is that this doesn't live on chain or anything. You're actually you're generating a proof and then using that proof as input to your smart contract methods. And so here, we're just we're defining a method here called fib sequence. So we're filling what ZK program wants is it wants you to fill in this methods object, and it's similar to how we were defining methods for a smart contract. So we define this method called fib sequence, And it has this method here which takes in n, which is similar to what we were doing before. And then it takes in these two proofs here. And the idea is that we're going to use these two proofs to build up a new state and then build a new proof on top of that. So we first want to verify that the proofs are right, and we just do that with .verify, which is pretty easy to do. And then we calculate our new state by referring to this like fib1.publicinput.add, fib2.publicinput. And we're just doing the same add call that we were doing before. These public inputs are field elements, and these proofs have public inputs that you can refer to. So you do it this way, and then you make the same assertion call that you did before. We're checking that what we calculated was the same, or is the same value as this n we're passing in. And then if those constraints pass, we generate the proof, and then we can submit it to our ZK app as input parameter. So here, we're just defining a class here. We're just like wrapping it in a proof class, and this is just some bookkeeping for SnarkyJS. And then the important part is this class at the bottom here. We're defining this Fibonacci sequence rollup class, which is extending the smart contract. So we're defining a new ZK app, and it has no state. And we're defining one method on it called verify. And it takes in as input the proof, that the ZK program that we just defined in the slide below. So the idea is that we can do all this computation work beforehand, calculate the Fibonacci sequence to some random or arbitrary n that we want, and then we can just call proof.verify in our smart contract and then continue with whatever we wanted to do before. So this is a really powerful technique because it lets you build certain applications that are a little bit complicated to write in a much easier way, since a lot of those details are abstracted out for you. So building rollups is really easy because all you're really doing is taking previous state transitions and then verifying them. And then you're producing a new state transition that's also easy to verify within your ZK apps. So that's basically like a quick rundown on how you write ZK apps, and I'll hand it back to Jack.
Thanks, Martin. That was awesome. OK, so yeah, to the end now. What is Mina? Mina is a layer 1 blockchain that proves its entire finalized state using recursive zero-knowledge proofs. And also, the smart contracts take the form of zero-knowledge proofs. Unlike other blockchains, the size does not grow, or I guess the size of the thing required to verify the current finalized state doesn't grow. It stays fixed at the size of 22 kilobytes. And so this is cool, but it's also useful, actually. Yeah, it's both cool and useful. And there's quite a few reasons. The first is privacy. Ethereum smart contracts run on every node, so all the information is public. Yeah, you can see here's an Ethereum example. If you want to make something private, you have to find a way to obfuscate something that's inherently public, and that's hard. Mina smart contracts run in the browser, and arguments and intermediary values are private by default. So the only thing that gets sent to chain when you submit, or when a user submits a transaction, is a state update and a proof. The other reason is scalability. There's no gas model. ZK apps run off-chain, so the amount of computation doesn't affect the transaction cost, and you can actually do an unlimited amount of computation in a single transaction. Developers can also use recursion to build these application-specific rollups that Martin talked about. And if you want a little bit more details about this, we have a mastermind example that's pretty simple and is linked to in a QR code at the end of this presentation. So there's kind of a lot of different directions you can move with this, and we hope that you guys will kind of explore that. But one thing that you can do is, like in the case of a game, you can have users play the game with each other, because really only the person you're playing with has to verify that you're making legal moves during the course of the game. And so that way you don't have to pay transaction fees or wait for blocks while you're playing the game. And then at the end, the whole game is verified by the chain. The other thing that's pretty cool is the decentralization. It's possible to validate the entire Mina state using only a small zero-knowledge proof. So there's no need to rely on trusted third-party node operators like Infura. It's possible to build wallets that basically verify the current finalized state. There's sort of no additional, the wallets behave like a full node from the perspective of like one account. It's basically a full node for one account. Another thing that's pretty cool is bridging. Because the smart contract, because the Mina state is proven using this small thing that can be verified in kind of a defined way, you can actually just write a smart contract on another chain that verifies this proof and then bridge all the information over to that chain. So there's no sort of like, I don't know, having some party of people vote on something. There's no like having like some sort of incentive mechanism and some money locked and like a slashing mechanism. It's just as simple as you submit a transaction. If the transaction is valid, then you can update the state on Ethereum. And actually, the NIL Foundation is working on one of these, and they have a version running on testnet right now. And so again, we have a link at the end of this presentation to like a web demo that you can do. So it will help you take the whole Mina state and bridge it over to, I think, Gorelli. The final thing that's pretty different about Mina is the way that we can do oracles. So in the future, users will be able to create TLS proofs that bridge data from any website onto the Mina blockchain. What this ends up looking like in practice is, basically we take this sort of TLS exchange and we prove the whole thing, and what we get out of it is like I guess like a version of all of the guarantees that it provides to users that's non-interactive. And so this is important because then we can, use it with blockchains. And the other thing that you can do sort of in the process here is you can take all this information and you can obfuscate it or do some sort of like augmentation of it. So if we wanted to do something like prove that we're over the age of 21, we could log into our bank account, prove that we did this correctly, then run some routine, like maybe hashing our social security number to prove that we're a unique person, and then prove also that we're over the age of 21 based on like our birth date field in the website or something. What else? Well, we actually don't know everything that's possible with this model yet, and so we're hoping that people here will help explore, because there's a lot of crazy things. Like, well, we can talk about them later. If you're curious, come stop me. But probably some stuff is possible that we're not really even aware of yet. Yeah, so in short, what makes Mina Protocol unique? Privacy. Applications run in the browser, so users have privacy by default. They run off-chain, and multiple interactions can be batched into a single proof, so it's more scalable. Clients can verify the finalized Mina state using only a small zero-knowledge proof and do not need to trust a third-party node, so it's more decentralized. You can bridge to other blockchains as simply as validating the most recent state proof in a contract on that chain, so interoperability is better. And the efficient verification of these proofs allows a new kind of oracle to really be usable. This is maybe I should have mentioned this. The key is that it's so efficient that it will be like economically viable to do these proofs of website interactions pretty regularly. With that said, how do you get started? It's actually really simple. We have only one piece of development tooling. It's called the ZK App CLI. All that it does is set up the TypeScript compiler, some scaffolding, linters, that kind of thing. So it stays out of your way, and it's very elegant and simple and easy to use. Yes, you can just npm install this and make a project. It'll come with a default contract in the scaffolding, so you can start playing around. And then when it's time to deploy, you just take this repository, push it to npm or something, and then you can import it into your UI. Ways that you can get involved. We have a quarterly grants program, or I guess Mina Foundation has a quarterly grants program, and it's backwards looking. So you can build ZK apps, you can make educational content, or you can do mentoring within the community. All of these things make you eligible for a backwards looking grant. And I think that's it. We have a QR code here with a Notion page that has all the relevant links from this presentation, links to the slides, that kind of thing. There's some other good stuff in there. If you have sort of outstanding questions, odds are that they're answered somewhere in there. You can join the ZK App Developer Discord channel. That's a good place to kind of stay in touch with people who are doing this kind of thing. You can follow us on Twitter. And I think that's it. I think we can open up to questions and answers now. Thanks, guys.
Hey, cool library. So for the recursive Fibonacci example, you took in two previous proofs as private inputs. So I have two questions. The first being, do these two proofs have to be of the same type, meaning proving the same relation?
No.
Oh, really? Cool. So in that case, you can do like can I express a circuit that like verifies an instance of itself?
I think so, yeah. Martin, do you have a definite answer on that? My answer is yes. This is the way that the Mina blockchain itself works, I think. Right, so the question is, well, I just want to make sure I understand the question. So the question is, like, we have a proof, and can the proof take its, so we have a program, and can the proof of that program be passed in as an argument to that program?
Yeah.
Yeah, yep.
Okay, cool, thank you.
Yeah, of course, thank you.
Thanks for the presentation. Yeah, I was wondering about the oracles, because that's a really cool use case. I'm wondering like what technology you use for that. Is it like a TLS Notary or Deco, or is it something entirely different?
Yeah, so it's something that we're building ourselves. Odds are that there's some overlap with the way that those things work, but yeah, it should be fairly unique once it's complete.
Cool.
I basically have the same question. So is
Yeah.
it a proxy, or is it something else you're not ready to talk about?
What do you mean by a proxy?
Oh, I mean, because it's, TLS is symmetric, right? So
Yeah.
So
there
how
is
do
a
you
third
deal
party.
with that?
Yeah,
Right? That's
yeah.
the
There's
big
a third
question.
party, just like
Third
in
party,
TLS Notary. Yeah.
Hi, great presentation.
Thank you.
If the Mina blockchain has no gas model, how do you handle, let's say, an attack vector where somebody could submit a proof with a very large public input if you don't charge for the size of it?
There is a limit to how much input you can feed into a transaction, basically. It's set, I think, like at the protocol level. And I don't think it would be hard to change. But the idea is if you have a proof that needs a huge amount of input, what you can do is, like, let's say, to kind of go back to the first question that we got about, can we verify proofs of themselves, I guess? Maybe that's not the right way to say it. But like, I don't know, let's say we want to prove something like moving average over a huge amount of time series data. We can take some chunk of that data, make a proof of it, and then feed it into itself, and then take another chunk of that data and do this recursively over and over again until we get a proof that commits to all of these inputs, but is the only input to this proof in terms of the transaction that you send to chain would be like the only argument you would pass into the smart contract on chain would be this one proof that's aggregating all of the constituent proofs.
Right, but how do you aggregate the public inputs in that case? Because if you have, let's say, like 10 different proofs and they all have different public inputs,
yeah,
you verify the total proof, you still need to know the public inputs.
Yeah, you can commit to the inputs in like, so you can have all of the inputs for this one proof. This proof can like compute some sort of commitment to these inputs and move up the chain that way.
Right, and then where does the opening happen then?
Where does what happen?
Where do you open the commitment then?
So I think if you want to talk about this after, that might that might make sense. I might have to think about this a little bit more in order to give you a good answer.
Oh, thanks, yeah.
Of course.
When you get the basically the previous commitments, the previous values that were inputs, are those actually proved down from the prior like root hash, or do you trust the miners to give you the right numbers?
Can you say again?
In the recursive proof example, you have the inputs that come from the previous proofs that are actually on blockchain. And I'm wondering if the prover, or at least the client, has to prove inclusion from the root hash, or do you trust the miner to give you the right values?
I'm not sure. I can get you a definite answer after this, though, for sure.
Can Snarky be used outside Mina? Like, can I use it to just build ZK circuits?
Yeah, so right now it's kind of designed primarily for use with Mina, but it is possible to define these, there's the smart contract class, and then there's this ZK program. And so these are, the smart contract class is specific to Mina, and the ZK program thing is just a ZK program. But realistically, all of it is designed to be used with Mina today. And this is kind of, we think that it makes sense to use all of this stuff with Mina. Like, Mina is kind of, maybe we envision it as like the final settlement layer for zero knowledge proofs. Like, you can do all sorts of crazy things. You can build data availability solutions. You can build these like hierarchical consensus models. You can build all kinds of really specific rollups. And you can interop with other chains relatively easily. So I think like in most cases, it will make sense to use SnarkyJS with Mina.
I have another question regarding bridge. Maybe you can go first.
No, you should go first.
So can you explain a bit more? Like, so you said that you can just verify one proof and be sure that sort of build a light client of Mina over some other chain, right? How do you know that this proof is actually the latest proof? Because you could have taken a previous proof.
Yeah. This will vary based on the bridge implementation,
right.
But the NIL Foundation has, I think, a couple of different, they have a paper, and I think they have a couple of different models for doing this. Yeah, there's not like a magical thing that solves that. It's sort of approached like the way that you would expect.
Okay.
So in the interest of time, because we're running a little bit over, let's direct all questions to during lunch.
That sounds great.
All right. And otherwise, let's thank our speakers.
Awesome. Thank you so much, guys.